Hello everyone. Thank you all for coming. So my name is Seemann, and you can probably tell. If you want to know more about me, there's information there at blog.play.dk, so I'm not going to tire you with any of that. This talk is called Fractal Architecture, as it says on the slide. And before I dive into the next slide, I think it's a good idea to just establish what sort of problem that this presentation addresses. So this presentation addresses the problem of software development productivity. I think most of us probably have the experience that we would like software development to be more productive, to happen faster, to be more responsive to user requirements and things like that. So that's this is generally the idea. It seems like we're not really doing. We could probably do better with software development productivity, and this talk tries to address this problem. I'm not saying this is the only solution, but I think it's a fairly important one. So why is software development productivity not as good as we would like it to be? And I think one of the reasons is that we spend a lot of time reading existing code. We actually struggle to read the existing code. And Robert C. Martin agrees with me. One of his books is writing, the ratio of time spent reading versus writing is well over 10 to 1. And I don't know where he gets that number from. I think he's just using it to illustrate a point. But at least I can accept with the general idea that there's a lot of reading going on. You struggle with understanding what existing code bases do in order to figure out what's the next line of code that I have to write. So if this is true, there's an opportunity for quite massive productivity improvement right there. So we can try to illustrate this by just lining a couple of boxes up. So here's 10 orange boxes and 1 green box. The orange boxes represent all the reading you have to do of existing code, and then the green box represents the writing of new code. So that's a 10 to 1 ratio. Now, often when people talk about development productivity, you'll have software vendors who will tell you that if you use their new tools, their new development environments, whatever that is, you will improve productivity. Or language designers will tell you that if you use a new language, that will improve your productivity. Or frameworks will improve your productivity. And most of those productivity gains are framed in the context of enabling you to write code faster. Now, just hypothetically, if you imagine that you had a tool that could magically slice the amount of time you have to write new code in half, that is not realistic, but just let's imagine that. That would look like this. So this would be, a reduction in time it takes to write code by 50%. So 50% sounds like quite a bit of an improvement in productivity, but really it's just, 4.5%. So. And don't get me wrong, I'll take all the productivity gains that I can get wherever I can. So if there's some vendor who presents to me a better development environment that enables me to move a little bit faster than I could before, I'll take it. But I think we should be under no illusion that that's not really where we kind of harvest the big improvements in productivity. On the other hand, if we can just slice off, one of those boxes in terms of, being able to read code, that's a much bigger improvement in productivity. So it would really be favorable if we start, thinking about writing code that also reads easily and be very explicit about that, because that's where improvements develop, productivity improvements are actually to be found. So how do we do that? So the problem is, I think everyone can agree that we should write, readable code. It's just that often if you leave it at that, you basically have what sounds like a subjective discussion. It sounds like a matter of opinion. Some people will say, I find this code readable, and then someone else will say, I don't find this readable at all. I think it sucks. And then the first person will say, but it's very readable. I wrote it. And then the next person will say, yeah, that's why it's not readable. So you can't have those sorts of discussions, right? It's opinion-based. It's subjective. That doesn't work. So instead we need to figure out, can we somehow make it a little bit more actionable, a little bit more concrete? Can we make it a little bit more objective? I'm not going to, promise you that it'll be 100% objective. It will not. I'm just trying to pull in that direction. So in order to write readable code, we should probably start to, just try to understand what actually happens in the brain when we're trying to read code. And I'm not a neuroscientist or anything, and no one really knows anyway. But we can have some, large picture explanations or descriptions of what happens when we read code. So I'm going to show you some code, and I'm going to talk quite a bit about this code. And what's important here is how we approach reading code. So even though I'm going to spend quite some time talking about this little code snippet here, it's not because I want you to understand the algorithm. I want to talk about what happens when we read it. So that's the important part. So I would claim that this is readable code. Not because I wrote it, and not because it's nicely formatted. Maybe you think it is, maybe you disagree, but because of other reasons. But let's start to think about what happens if we read code. So first of all, I think most of us start from the top and go down. So you'd say, okay, this is a method called allocate. It takes some reservations as input. I don't really know what reservation is, but maybe I can figure that out later. It returns IEnumerable of table. I don't really know what table is either, but I can probably figure that out if that turns out to be important. So all the code that you see in this talk is taken from my book, Code That Fits in Your Head, and it's my patented online restaurant reservation system example that I always use. It's not patented. It's just something I said. So after you figure that out, you just move on and you say, okay, so here's an object. We take some tables, we turn it into a list. A list of something in .NET, so this is C# code. A list of something is a collection of things that can change. You can add more things to it. You can remove things from it. You can sort it and do various different things to clear it out altogether. So it might change state. And if we're trying to understand what's going on, that's probably a good idea to just keep in mind, when we read the rest of the code, because maybe the state of this allocation will have some impact on how the code executes. Turns out not to be the case here, but it might. You don't know until you actually read through the code. So there's one thing to sort of keep track of in your head. So basically what's happening here is you're running a little emulator, you're running a little C# interpreter that interprets the code, not on the computer, but in your brain, and you're sort of trying to figure out, okay, what would happen if various different things. So for example, you might say in the next line, with the for each thing, you might say, well, what would happen if reservations is empty? In that case, you would just drop all the way through and return the allocation. But you're still keeping track of, what's the state of allocation? What's the state of that collection? Now, on the other hand, you might also imagine in your brain when you're reading the code, okay, so what's going to happen if that collection is not empty, if we have some reservations, in which case the code sort of takes a different pathway through the code there. And then, there's this thing where we try to find a table in that allocation. And again, there's a branch, there's a decision to be made. So that little thing, if table is curly brackets, that's a C# sort of a little pun expression that basically means if table is something as opposed to null. So when we're trying to find a table, it might be null, and if it's null, if it's not something, again, nothing more is going to happen. So on the other hand, if we find a table that fits the desired quantity, we now go and modify that allocation collection. We remove the table, but then we add it back just with the reservation associated to it. So we reserve the table to that particular reservation. Yeah. So this is not hard to follow, and you'd say, well, okay, so even though we have some state mutation going on in that one object that we sort of kept track of in our head, we now understand that even though it changes throughout these loop, at least the number of tables stay the same, because we always first remove and then add something back in. So it's the same number all the time. So there's at least two types of quantification going on here, or attempts at making things a little bit more concrete. I've counted the number of pathways through the system. This is called cyclomatic complexity, and you can say, well, it's a way of thinking about the various different pathways through the system, but you can also think about it as it's basically three parallel universes where the code might take one or three pathways through, and you sort of have to fit those three options, those three parallel universes in your brain at the same time in order to understand what's actually happening here. And then you need to keep track of at least one thing because allocation might change state. And in this case, it turns out that it doesn't impact the execution. It doesn't make any impact on decisions. But you didn't know before you actually read through the code. So I would say this code fits in your head because there's not too much going on. There's sort of three pathways, and there's basically one mutable variable that you need to keep track of. So that's not too much. Now. So the next question is, what is too much? What's the threshold? If I say 1 is fine, if I say 3 is fine, when does it become not fine? Is 10 still readable if we had 20 things going on? Would that be readable? And I would say the threshold is around 7. And this goes back to a results from experimental psychology. There's a paper by George A. Miller from 1956 called The Magical Number 7 plus minus 2. You've probably heard about it. And it's one of those few results from experiments in psychology that actually seems to be fairly robust. So Miller did a lot of experiments with subjects where he asked people to remember, all sorts of things, numbers and things like that. And he found out that most people could keep track of about 7 things. And then if he asked them to keep track of much more than that, they started to forget some of the things that were not as present in their memory. So in general, Miller asked people to remember all sorts of numbers, but he also asked them to remember other things. So for example, names of colors or things like that. And he just called that those information, he called them chunks. There's chunks of information. Now I'm just going to switch over here and start a little animation while I'm still talking. I'm just going to keep talking then. So the problem is with the software development is that if you write a completely brand new code base and you start with hello world, there might actually just be that one thing going on. But as you add more features and more things that the software can do to your code base, there's going to be more and more things that you need to keep track of. So in a realistic code base, there's more than 7 things going on. There's probably 7,000 things going on, 7 million things going on in a realistic code base. And that doesn't fit in your short-term memory. So we need to figure out, how do we deal with that sort of problem? So the reason why I started this little animation is, as you can tell, it just keeps on adding chunks. The chunks appear randomly every second or so, and they appear, on the outside of the screen, so either to the left or the right or the top or the bottom. And you will also notice that these chunks sort of try to arrange themselves so that they try to keep as much distance to each other as possible. But we just keep adding more, just like we would, if we start in a new code base, we would keep adding more and more decision points, more and more things that, in order to understand what the code does, we would have to keep track of that as well. So we don't structure the code in the way where we don't just start with a main method and then just write a main method that just runs forever. We structure code in various different ways by dividing it into objects that communicate with each other, routine, functions that call each other, and so on. But one of the things we need to figure out is what's a good way of structuring code so that it remains readable. So that it fits in our short-term memory. Even though there's not only 7 things, but there's maybe 7,000 things, and you can see, I'm not going to reach 7,000 things or 7 million things here. That's not really what I'm waiting for. But you just keep on adding and more stuff. So we need to figure out, how to structure code so that we respect that cognitive constraint that our memories have. I remember, once I was talking to a person. I was engaged with a client that had a legacy code base, and I got the chance to talk to some of the developers on that legacy code base. And I asked one of the newest member of the team. I asked him, so how much time did it take you before you felt that you were able to work in this code base on your own, independently of your colleagues? And he said, it took me 3 months before I actually felt confident to work on this code base on my own. So when you have legacy code bases like that, there's a lot of stuff going on, and the strategy you take when you try to learn a code base like that, that does not employ short-term memory. So this developer who took 3 months in order to be, to be able to work with that code base, he probably painstakingly started to commit the structure of this code base to his long-term memory, which is a completely different game. But the problem with relying on your long-term memory instead of your short-term memory is that, first of all, it takes a long time. So that's why we spend so much time always reading code, because we have to engage our long-term memory, and it's much slower. And also you have the problem with long-term memory that once you've committed something to long-term memory, it's hard to get rid of again. And that means if you've committed the structure of a code base to long-term memory and then you go change it, then what you've learned about the structure of the large-scale code base no longer really applies. And then you sort of have to unlearn it again, which is also difficult. Now, short-term memory, on the other hand, is much more efficient in this way, because if you learn something and you keep track of something in your short-term memory, you work with that, and once you're done with that, you basically just forget about it, and the next time you look at something, you just basically load it into short-term memory again, look at it, and forget about it again. Now, as you probably noticed, these blobs, these chunks that just keep on adding here, they sort of start to form a honeycomb pattern, a hexagonal grid. So if we wanted to pick out just 7 of those, we'd had a shape that looks pretty much like this one. So I call this a hex flower. I think it looks a little bit like a stylized flower in the sense you have 6 petals and then the center of the flower. But what I'm going to use this for is it's just a symbol of our short-term memory capacity, because we have 7 cells there. So you can imagine that those are registers where we can each register can hold 1 chunk of information, and we can hold about 7 of those. Again. I know that it's 7 plus minus 2, and this diagram doesn't allow 9, but this is not, again, this is not a hard thing, it's not science, it's more like, a way of illustrating a point. And it's pretty. We also need to realize that, if we're looking at code, there's a lot of abstraction going on. So inside of each of those cells, there's probably going to be more stuff going on. So if we structure the code in such a way that there's at most 7 things going on, we can structure the code so that it fits in our short-term memory. But again, we should probably realize that, if we're thinking about layers of abstraction, each of those cells will again contain some more code that does something else. So you can keep on zooming into one of the cells, and maybe finally you'll find a piece of code like this one. So this is I chose this create method. This is sitting on a repository class that communicates with a relational database and actually saves reservations into the database. And I chose this one because this is about as much as you can zoom in terms of layers of abstraction. There's really nothing. There's no more layers of abstraction hidden behind this code, not in terms of user code anyway, because there's still framework code, there's SQL connection, SQL command, and things like that, but there's not really a lot of my own code. So this is sort of like as granular as it gets in terms of levels of detail. So we could ask ourselves again, is this code readable? And instead of being opinion-based, what we wanted to do is to say, let's try to quantify it, not because we want to turn it into science, but just to be able to have a discussion that is a little bit less opinionated and a little bit more about some facts that we can actually bring to bear and discuss things about. So we could ask ourselves, for example, what's the cyclomatic complexity here? How many different pathways do we have? And there's only 2, because either you immediately exit throwing an argument null exception, or you run through the rest of the code. So cyclomatic complexity of 2. That's okay. If we think about cyclomatic complexity as representing sort of parallel dimensions of the code, 2 is not that's not a lot if we can keep track of 7. We could also ask ourselves something else. So you remember one other thing I talked about is I talked about when we read code, we sort of run a little emulator of the language inside our head, and we try to keep track of state. So what we can do is we can try to count the objects that are involved in this method, because in an unsophisticated, naive way of counting this, everything is a priori something that may change state, and then we can become a little bit more sophisticated later on. So let's try to just count objects to see how How many things, how many chunks are involved in a little code snippet like this? So there's the restaurant ID, that's one object, one parameter. There's reservation, that's 2. We have a thing called connection string, and it's, in this code snippet, you can't tell exactly where that comes from, but that's a read-only property. It's a string. Now, if some of you are not C# developers, a property is just a glorified class field. So just think of this as a read-only class field. That's basically what it is. And it's a string. So this just contains the information about how do we connect to the database. And we use that to create a con object, a connection object. I'm just counting things here. There's also something called create reservation SQL. This is another string. This is not even a read-only property. This is a constant string. It's just the actual SQL, the T-SQL language that's going to be applied to the server when we run this command. So another string. And we use that to create a command object. And then that's actually it. There's no more objects involved. The rest is just manipulating those objects. So there's 6 things. And again, if our memory capacity is 7, that's just about it. We're good. So again, this is a way you can discuss, for example, if you're discussing with colleagues, is this method getting too complicated? Should we split it up into 2 helper methods or things like that? And you say, well, what's the criterion? When do we start splitting things up? When do we start refactoring? And I would say you start refactoring when some of those quantification mechanisms begins to indicate that the code is becoming too complicated. And 7 is quite a low threshold, but it actually enables you to keep the code fairly fresh and clean if you go with that sort of threshold. So if we want to be a little more sophisticated, you might then argue, you might say, well, okay, so that's all fine, but if you take, for example, the restaurant ID, the one labeled 1, that's an int. And you don't need to keep track of, an int if you're trying to remember or keep, running this little emulator in your brain. You don't have to keep track of, what restaurant ID might, change into, because it's an immutable value. It's not going to change. So immutable values are really nice for that particular reason. So they don't really tax your memories that much because it can't change. So the same thing goes for strings. So connection string and create reservation SQL, those labeled 3 and 5, those are strings. They're also immutable in .NET, which means they can't really change either. So you don't really have to worry too much about, might this one object change state while the code executes? It will not. It is immutable. So that's actually like 3 out of 6 things that are not really going to tax your memory. So you say, well, okay, that actually turns out that immutability is a really nice thing in terms of readability, because that means we don't really need to worry about them changing state. We should do more of that. And I did. So it turns out if you go and look at this code base and look at reservation, the one labeled 2, this is a custom domain class that I wrote, but I wrote it so that it's a value object, it's an immutable data structure. So also, it's not going to change state. So really the only 2 things that might change state in this code is just the connection and the command, just 2 things. And you can see that actually happens, just below, after we created the command, we start adding, binding parameters to it. So it actually mutates 6 times. But it's easy to follow because it's sort of doing the same thing over and over again. And then in the last, in the penultimate line there, we open the connection, so the connection changes state as well. But it's easy enough to follow because even if you want to be unsophisticated, there's only 6 things going on, and in reality, there's only really 2 things you need to keep track of. So if the memory limit is 7, then we're all good. So we can enumerate the objects in this way, or we can try to assign them each to one of those cells that we have in our short-term memory, and we say, okay, so we have room for 7, and this is only 6. That fits in our head. So again, you can think of this little figure, this little hex flower, as just a symbol for things that fit in your head. So I started by showing you the lowest level of detail. I showed you this create method where there's not a lot of extra abstraction hiding behind that create method. It just talks to the relational database SDK. But then you might probably say, well, but there's going to be code that calls that create method that we just looked at. And that code is probably going to call some other methods as well that have some moving parts inside of it. So doesn't that mean that, that complexity that is inside the create method and the complexity that's inside some of the other methods, doesn't it mean that those things are going to compound? So, it's fine enough, if you're at the lowest level of detail, but what if you're at a higher level of detail, then how do you deal with that? And the thing is, again, our memory constraint, the cognitive constraints that we have in our brain, it's not going to change. It's 7. So we have to sort of work within that boundary and figure out ways to do that. So even if we zoom out and say, okay, so now I'm looking at things from a higher level of abstraction, we still need to respect that we have this cognitive constraint. The brain is not going to change anytime soon, regardless of what Kurzweil is believing. I don't think that's going to happen. So we should be able to zoom out and zoom out and zoom out, and we should be able to zoom out all the way to, for example, the entry point of the application. And even if we look at that, it should fit in our brains. We should understand. We should be able to understand what's going on at a high level of abstraction. In our short-term memory. So if you've ever seen ASP.NET code, this is basically just generated by a wizard. I didn't write this code, but still, you might want to count. Does this actually fit in your head? And it turns out it's actually pretty simple. All the interesting stuff happens in the startup method. We can look at that at the moment. So there's really only 3 things going on. There's only 3 objects involved. So that's well within capacity. So that's fine. The point here being that if you want to look at what happens in the startup class, though, at all levels of abstraction, we should respect the cognitive constraints of our brain. So when I look at the startup class, it should be structured in such a way that there's at most 7 things going on. And that also means startup should be independent of arcs and web builder. When I go and look at startup, I shouldn't have to also remember that there are things like arcs and web builder. So we can start by looking at just the public API of the startup class, and we can say, okay, so by convention, there's these 2 configure methods. There's a constructor that takes an iConfiguration value. That's sort of like those 2 things go together. So again, if we want to enumerate them in that way, that's good. Again, at that level of abstraction, it's understandable. And then if we want to look at configure services, we can go and start to examine that. And again, if we want to do a little bit of a quantification, we say, well, is this readable? Meaning, does this fit in your head? We can start to, again, quantify it and say, well, for example, what's the cyclomatic complexity here? And there's no branching, there's no looping, there's just one straight line through the code. So cyclomatic complexity is 1. I know you can't see all the code. It goes a little bit beyond here. I'm going to scroll in a moment, but I promise there's no surprises there. So cyclomatic complexity of 1, it doesn't get any better than that. What if we start counting the objects again, just like we did the last time? So I'm not going to do that quite as detailed an analysis as I did the last time, but you notice there are 6 things involved. So again, we're good. It fits in our short-term memory. This is still a very high level of abstraction, so you're getting a little bit more detail about how the software is structured. So again, the point here is I'm not trying to teach you how I wrote the code. I'm trying to teach you how to structure code so that it becomes discoverable and it's readable. So if you're trying to sort of figure out, how do things work in this particular code base? For example, let's say you're interested in knowing, what are the security mechanisms? Do I need to log on into this system in order to use it? You probably say, well, maybe I can find some information there and configure authorization. And then if you go there, your expectation should be that, again, that code is structured so that there's at most 7 things going on. And all the stuff that you're looking at right now should now, go out of scope, basically. You shouldn't have to know about any of this stuff that we're looking at the moment. And if you want to know about, how does persistence work, you might say, well, we could also go and look at configure repository. That sounds like a place where I could get a little bit more information about that. And then again, if you go and look at that, what happens inside of configure authorization, for example, should become irrelevant. So here's another way we can this is a little bit more of an ad hoc quantification, but the point is that, you should structure code so that, you always have this, this appropriate level of, this appropriate amount of information at the level of abstraction that you're looking. So one thing you might wonder now is, I sort of hinted at this before, there's this remaining problem of saying, okay, but if we have at the lower level of abstraction, if we have something like the create method where there's 6 things, 6 objects being activated, and cyclomatic complexity of 2, that's not too bad. But then if we compose those methods with other things that also have moving parts, what prevents those things from compounding so that instead of we only having 6 things going on, we have 18 or 25 or 100 things going on. We really need to be able to let those things that at one level of abstraction have something going on. When we look at it from the higher level of abstraction, they should just present as one thing. We should be able to think of them as a chunk of information, not several chunks of information, but just one thing. So the question is, how do you do that? And the high level answer to that is good API design. And there are lots of, there are thick books about, how do you do good API design, and all of them have, most of them have pretty good recommendations about that. But I want to do something a little bit more concrete here. So I'm going to look at one particular method, and I will claim, and I will now make the argument that this not only fits in your brain. We're going to look at the allocate method. I'll make the argument that not only does this fit in your brain, we've sort of already been there, but I will also make the argument that when we look at it from the outside, this presents as one chunk of information, and only one chunk, even though there's actually more stuff going on. So we did establish that we have a cyclomatic complexity of 3, and we also did establish that we have some stuff going on. Actually, if you want to count all the things that are involved, there's actually 6 objects, but there's only one of them that has the potential to mutate. But if we want to be unsophisticated, we could say there's 6 things going on, and at least also a cyclomatic complexity of 3. So we can't really afford any of this complexity to escape this abstraction scope that we're looking at. So at this level of detail, it's fine, we can deal with it. But if we're looking at the allocate method from the outside, we can't allow stuff like these implementation details to escape, because if we have to keep track of all of those 6 things, plus whatever happens in other method calls, it's not going to fit in our head. It's not going to fit in our short-term memory. So we need a way to figure out that this collapses into being just one chunk of information, one abstraction. And I will make the argument that that's the case here. Why is that? It's because I've very deliberately written this method so that it has some properties that are very desirable. So first of all, it has no side effects. Some of you will already know where I'm going with this. Let's just go back and look at that. It has no side effects. What's a side effect? A side effect is something that changes the observable state of the universe. So if you send an email, that's a side effect. If you add a row to the database, that's a side effect. If you repaint the screen on your computer, that's a side effect. Basically, you can't do anything interesting with a computer without producing side effects. So it's not that we don't like side effects, but we just want to be very deliberate about where we put them. And we want to avoid them most of the places. But this one doesn't send email. It doesn't add rows to the database. It doesn't write to the console. It doesn't write to disk. There are no side effects here. So it's a side effect-free method. So that's one property, and that's a nice property all by itself. Now, when I say property here, I mean quality, trait, characteristic of the code. Now, another property that this method has is that it's deterministic. For the same inputs, it's always going to return the same outputs. There's no randomness going on here. There's no random object. There's no access to the system clock. We're not asking about date time now or anything like that. We're not doing anything that might introduce some sort of non-determinism. We're not reading from the console. We're not querying third-party web services or anything like that. We're not even querying a database. We're just making calculations. This is an algorithm. So it's side effect free, and it has it is deterministic, and we have a name for that. That's a pure function. And the interesting thing about pure functions is that they are what we call referentially transparent. So that's a big word, but what does that mean? So referentially transparent, that means that a function call is equal to its result. So think about how you do arithmetic. You probably learned to memorize the multiplication table when you went to school when you were kids. So if someone asks you, what is 4 times 5? You just say, well, that's 20. It is 20, right? I'm really, really bad at this. But what you don't do is you don't actually perform the calculation, because how do you calculate 4 times 5? Well, you take 5 and you say 5 plus 5 plus 5 plus 5, and you can add them together. That's actually the calculation, but that's not what you do. You just memorized the result. And you can do that because multiplication is also a pure function, and it means you don't have to perform the calculation. If you know what the result is, that's just as good. So you don't have to run the function if you already know the result. So referential transparency means that the function call and the result that it produces are equivalent. Conceptually and also cognitively, we can think of them as being the same thing. So this means if you have something like allocate here, what's the result? Well, it's an enumerable of table, and it's a collection of tables. And you can think of that as just being one chunk of information. So if you want to look at the allocate method from the next level of abstraction up, it just collapses into being a value. It's a collection of tables. We don't care that it's actually a calculation with some execution steps. It's just a value. And because of referential transparency, we know that this is true. So functions are awesome. Do more of those. Doesn't mean that you can completely avoid having side effects and non-deterministic code and all sorts of things like that. But the more you can sort of put the things that are not pure functions in very specific places and be very deliberate about how you structure that code, then for the rest of the code, if you can keep that as pure functions, you know that all of that is going to collapse well into just the result value. So they're going to be, they abstract much better in terms of code that fits in your head. Right. So again, I want to reiterate that, at all levels of abstraction, we need to respect the constraints that our brains actually have. So we should be able to zoom in, and again, at that new level of detail, there should be at most 7 things going on. We should be able to zoom out, and at that level of detail, and even at the entry point, there should be at most 7 things going on. All right. Let's zoom in again, because I like this animation. All right, so again, here's another way to illustrate the same point. So I know I'm saying the same thing, but the illustration is going to be slightly different here. So at any given level of abstraction, we know that we have to respect our cognitive constraint. There can be at most 7 things going on. We also understand that behind each of those cells there might be more complexity hiding. It's just being abstracted away, and one way to abstract that away is by using pure functions. But there are other principles of API design that also enable you to abstract things away so that they look like one thing. The composite design pattern, for example, might do that for you as well. So another way to diagram or to illustrate that is to say, well, at one level of abstraction we have 7 things going on, but we also understand that at the next level of abstraction there might be up to 7 things going on in each of those 7 cells. So at the next level down there might be up to 49 things going on. Not that that fits in our head, but we understand that that's the case. But then we also understand that in each of those 49 cells, there might be up to 7 things going on, and so forth and so forth. So that's a fractal. And if you came and you thought fractal architecture and you were expecting something with Mandelbrot sets and so on, you might be a little bit disappointed and say, that's not really a fractal. And if you don't think so, let me give you something else. This is called a cock snowflake. And it sort of follows the same principle where we start with a very simple geometric structure, and then we keep on subdividing each of those straight lines into something that looks like that. And you can keep on zooming in on the edge of the cock snowflake, and if you render as you zoom in, you can keep on seeing the same structure repeating itself over and over again, infinitely deep. And the same thing is true here. You can keep on zooming. So I stopped the rendering at 4 levels, at 4 layers, because if I add a 5th layer, it basically just becomes one big green blob. You can't really see the laziness of it anymore. So this was just for aesthetic reasons that I stopped rendering there. But you could, conceivably, you could keep on zooming into these hexagons indefinitely, and you would be able to always subdivide them into 7 more hexagons. So that's a fractal. So that's why I call it fractal architecture, and also just because it sounds cool. So the point being, we need to respect the constraints that our brains have. In the short-term memory, we can only keep track of 7 things. Long-term memory is a different thing, but long-term memory, relying too much or relying exclusively on long-term memory in terms of working with code bases, I believe that that's where it leads us to the point where we waste too much time reading existing code because it's really difficult to understand. So I've been trying to write code that has, that is composed of lots of very small functions, and I've done this for years, and I find that it's not a magic thing, but it really makes a great difference in terms of how readable and how understandable the code turns out to be. So understanding these cognitive constraints allows us to write code that fits in our head. So, which is also the title of my new book, Code That Fits in Your Head, and you can get it wherever good books are sold. So that's basically what I had in terms of a presentation, but I know I also have some time left still, and I did this deliberately because I'm happy to take questions and do some answers, or answer those questions. So what I also did is I actually brought a copy of the book, Code That Fits in Your Head. It's right here. I also brought a copy of my previous book, Dependency Injection, Principles, Patterns, and Practices. No, Principles, Practices, and Patterns. I can't remember the order of it. That Stephen Durson and I wrote a couple of years ago. And I also brought an old T-shirt, an auto-fixed T-shirt, if anyone is interested in that. And I plan on giving them away to people who ask good questions. So basically, I'm just saying, well, the first person who asks a question gets one of those things, and so on. And if you're asking, Mark, what's your favorite color? That counts as a question, but you don't earn a book from it. Ask a good question, right? So any questions? Yes, sir.
So when coding C#, for example,
Uh-huh.
how do you signal to your fellow programmers that this is a pure function? You don't have to go into it and look for side effects.
Right. So the question is, if you couldn't hear it in the back, if you're writing in C# or basically any other mainstream language, how do you signal to all the other programmers out there that this is actually a pure function? You should understand that this is a pure function. And the short answer is there's no technical way of doing that in C# or in Java or on any other mainstream language. So you have to rely on some sort of out-of-band communication. So either put a comment on it or just talk to people and say this is pure or whatever else. If you're interested, I actually wrote I did write a blog post about that, so let's find that. I think I can find my blog here. What did I call that though? Oh, bloody hell, I can't remember. Maybe I can search myself. Okay, so I'm not going to spend too much time on this. Let's see. Oh, no. Okay, I can't remember. I'll put it on. Are you looking at the Slack channel for the session here? If you are, I'll find it and I'll post it on the Slack channel. Does that work for you? I can't remember the title right now. Okay, sorry about that. But the slightly longer answer to that is still that, let's start this up again. The way that these languages are designed, you sort of need to, at least the experience we have from Haskell. Haskell is one of those languages that actually just does distinguish between pure and impure. And it's built into the language in a very specific way. And it's something that is very hard to retrofit into other languages. You sort of need to design it in from the start. There have been attempts to use attributes, where you can put a little pure on top of it, but you don't get any sort of compiler checks on it, so you're really on the honor system anyway. But I think it's a good question. Which one of those things would you like? 2 books and a T-shirt. And the T-shirt is a little... Which one? Right, okay, so congratulations with that. Yeah, it's not a draw, but I think my publisher likes me to give these things away because it makes it more desirable. So now you didn't get it, you have to buy it. Yes, sir.
So you mentioned that if you have 2 chunks, they shouldn't know of each other, right?
They shouldn't know of each other?
Yeah, so you shouldn't need to go to see what the other chunk has
Mm-hmm.
to understand what
Right. Okay. So if I understand you correctly, you're saying, well, chunks shouldn't know of each other. So how do I keep things separate? But there's probably still going to be dependencies, between things. You can't write everything so that they're sort of standalone. Sometimes you need to leverage, other things. And I think it's if I may be so bold, I think it's a little bit of a misrepresentation of what I said, because that's not quite what I had in mind. I'm just saying whenever you look at a piece of code, there should be few enough things going on in that piece of code that you can understand, that it fits in your short-term memory. But if there are 3 of those things are somehow connected to each other, that's a thing you'll be able to understand if there's not a lot of other things going on. But then if you maybe you mean by your question is saying, well, okay, so if I have one thing, but that actually it has a lot of dependencies that calls into other things. Is that what you had in mind? But then again, this is why I think, often pure functions save you, because again, even you can have a pure function that calls other pure functions that calls other pure functions, and maybe if you try to, if you try to summarize all the complexity that's going on inside of that, top pure function, you might have cyclomatic complexity that is, several hundreds of things. But still, because it's referentially transparent, it just collapses into its result. So you can think of it as equivalent to the output that it produces. So you don't really have to worry about, how it arrived at that conclusion and which dependencies it had. It doesn't really matter at a higher level of abstraction. Does that answer your question? Okay. Would you like a book or a T-shirt? Not of that one, no. You will take the T-shirt, okay. All right, so the T-shirt has never been used. Okay, I'm selling it really well, but you probably want to wash it because it's been lying around. I found it in my cupboard, recently, and it's been lying around for a long time. So it looks a little iffy, but just wash it. I never wore it. Okay. All right, good. So do we have more? Yes, sir. So you're saying, do we follow the single responsibility principle here, or?
I'm just saying, if it is an issue for having some normalizing for a single responsibility method classes and so on, it is an issue or it is still the same?
I'm not sure I understand the question here. Yeah, I'm sorry. You kind of lost me there. I'm sorry. Maybe if you find another way of putting it, tweet me or write me an email or something like that. I'll be happy to help you out if it. Yes.
Can you apply that self-similarity rule to the classes?
Can I apply that rule to classes as well? Yeah, I think you can. That I tried to do a couple of illustrations with that, where we looked at, we start by looking at the startup class, for example, and saying, at that level of abstraction, just looking at the public API of a class, does that look like it's sort of a coherent thing? I tend to not that much, look at that. I'm more interested in looking at methods of functions. Because sometimes I think, I have a couple of examples in the book where I have a class that actually turns out to have like 7 or 8 members, but each of those members are fairly self-contained. So you can almost imagine that you can slice them up and understand what each of them does without understanding any of the other ones. It's mostly analysis mechanism or analysis method that I use to look at the actual code in terms of implementation. I have in the book and in the workshop I also hold that I give based on the book. I have a lot of other design principles where I talk about what's a good design principles in terms of API design and how do you design interfaces and classes and so on. And they go hand in hand pretty well, but it's not quite this way of looking at it. It's sort of complementary to that. But if you would like the book, would you like one? All right, thank you. Okay, so I'm out of giveaways. But that doesn't mean that I'm not, I'm absolutely happy to take more questions. I'm also mindful of your time. But we actually do have 10 more minutes. So if you want to have questions, then feel free to ask. If you want to get ahead and out of the room before everyone else, I can completely understand that as well. So any more questions? Yes, sir. No worries.
You were talking about purity in Haskell. What's your personal opinion of why isn't Haskell more used in
Right, yeah. Okay, so the question is, I talked a little bit about Haskell and how it distinguishes between pure and impure code. So what's my personal opinion on why is Haskell not more popular? That's your question, right? No, I'm just making sure that I paraphrase you well, because I think people in the back probably couldn't hear you, and because I have the microphone, you don't. So not your fault at all. Haskell is a wonderful language, but it's also really difficult to learn. And I think you could probably do things to make it easier to learn, but the way that Haskell is often being taught, it sort of puts a lot of people off. And it's also, the way that you often teach Haskell, it's probably a little bit difficult to understand if you're a beginner programmer. It's a little bit hard to understand why do we need to jump through all of these strange language constructs in order to achieve simple things. Just if you want to do simple I/O, write to the console or write to disk and so on, there's actually a lot of machinery that you have to understand in Haskell in order to do simple things that in other languages will just be console.writeline. So if you, and you're often, beginners are often impatient, they just want to learn and get things to working, and Haskell sort of, very deliberately prevents you from having things that works, basically. So I think that's one reason. I actually wish that it would be much more useful, or much more used in industry, but it's not. And I don't think it ever will be. But it's a wonderful thinking tool. I basically, I've worked so much with Haskell now that I tend to think in Haskell when I problem solve. And then when I've sort of thought things through and maybe done a little prototype in Haskell, then I would go and re-implement things in F# or in C# instead. So I definitely, if you're interested in functional programming, I would recommend that everyone sooner or later learns Haskell, because it really gives you an insight into what functional programming is that no other language will give you. So for that reason, I think it's really important. But only if you're interested, because it will require significant investment of your time. And I think also that's why it's not more popular. So I hope that's the best answer I can give you. And I don't want to tire anyone else with rambling on. So we can always talk about that. If you want to talk about this more, then find me in the break, and I'm happy to discuss this more. Anyone else? I'm quite blinded by these things, and it looks like there's no more questions, which means that you get out of here 6 minutes before time. Isn't that wonderful? So thanks for coming, and I hope you have a great conference.